Alright, we're going to look at the calculation that involve in the topic of measurement technique. Okay, where we're going to find out how to calculate the fractional uncertainty, percentage uncertainty, and the most important is the absolute uncertainty. So I found out that many students are having problem in calculating the absolute uncertainty for a physical quantity, which is you need to calculate using a particular formula. Okay, so this is what we're going to discuss for today's lesson. Okay, so let's see a particular physical quantity, say length, right? So let's say we have an object here, right? So say the length L is 10.0 plus minus 0.1 centimeters. And the width, so this is the length, and the width is, say, is about 5.2 plus minus 0.1 centimeter. This particular value is when we do this measurement, right? I'm just giving an example where it depends on the accuracy of the measuring tool. In this case is the meter rule, where the meter rule's accuracy is 1 millimeter or 0.1 centimeter. So this particular value, the accuracy of the value is given by the accuracy of the measuring tool, which in this case meter rule. Okay, hence if this is 0.1, which is 1 decimal point, so the measured value in this case, the width must be also 1 decimal point. Okay, so the length L is 0.1, 10.0 plus minus 0.1 centimeter. So the fractional error, fractional uncertainty, delta L over L is 0.1 over 10.0. Okay, so which in this case, will give us 0.01. Okay, or if we take the percentage uncertainty, okay, meaning that we take this value delta L over L times 100%. So 0.01 times 100%, I will get 1%. Okay. However, if you take the, you repeat the same process for the width. Okay, so the fractional uncertainty for the width, WL over L, which is 0.1 over 5.2. So you will find out that you will get 0.019, and the percentage uncertainty for the width is 1.9%, okay, which is more than the percentage uncertainty for the length. Okay, so we can say that the percentage uncertainty for the width is more than the percentage uncertainty for the length, right? The reason is because of the range, right? So in this case, the length has a bigger range compared to the width, hence making the percentage uncertainty lesser than the percentage uncertainty of the width. Okay, that shows that if you have a larger value of measurement, it will reduce the percentage uncertainty, okay, making the reading more accurate. Now let's try a different case, all right? Say now the width of this object, okay, I repeat the reading, I repeat the measurement using a vernier caliper. So vernier caliper, it has an accuracy of 0.01 centimeters. So example, now the width that is being measured by the vernier caliper, okay, is 5.22 plus minus 0.01. So this is just an example, okay. So it's the same physical quantity, but we are using a different tool to measure, right? So initially we use a meter rule, which has accuracy of 0.1 centimeter, but over here, the vernier caliper has accuracy of 0.01. So the percentage uncertainty for the width that is measured with the vernier caliper is 0.01 over 5.22 times 100%, which now we will get 0.1%, right? So that is far much more lesser or smaller than the percentage uncertainty of the width being measured by the ruler. So the reason is because of the vernier caliper, right? So if you use a more sensitive tool, you will find out that the percentage uncertainty becomes even smaller, okay, for the same physical quantity, right? Okay, the next part is that if you have example, how do we calculate the absolute uncertainty for a given physical quantity, right? So say U is a physical quantity, okay, that is being calculated using measured physical quantity, okay, such as X, Y, or Z, okay. So X, it has its own error, which is plus minus delta X, Y plus minus delta Y, Z plus minus delta Z. So for the first case, if U is equals to X plus Y, or U equals to X minus Y, hence delta U is equals to delta X plus delta Y for both cases, okay? Right, so whether it's addition or whether it's minus, so we add the error. Now for the second case, if U is X times Y, or U is X divided by Y, so the absolute uncertainty, delta U over U, is equals to delta X over X plus delta Y over Y, right? So this is the fractional uncertainty. Fractional uncertainty for U, okay? And the third case, if U is equals to X power of P, and P is a constant, so delta U over U is equals to P delta X over X. Okay. Now example, for example, let's say area is length times width. So the fractional uncertainty for area is the fractional uncertainty for length, and we add up with the fractional uncertainty for the width. Okay. And say example, volume of a sphere. Okay, so volume of a sphere is 4/3 pi r cubed. So the fractional uncertainty for the volume is 3 delta r over r, where r is equals to r plus minus delta r. Right, so take note the constant is not being carried forward in the calculation of the error, right? However, r power of 3, like we follow here, x power of p, so the p multiply with the fractional uncertainty of x. So in this case, 3 multiply with delta r over r, okay, which in this case is the fractional uncertainty of the radius. Okay, let's see another example. If you're given let's say a cuboid, where this is the length, this is the height, and this is the width. Okay, so the height is 2.3 plus minus 0.1 centimeter. Assuming that we are measuring all these measurement, right? The height, the width, and length using a meter rule, which has a accuracy of 0.01. Width is 5.6 plus 0.1 centimeters. And the length is 10.2 plus minus 0.1 centimeters. Okay, and if you're asked to calculate the volume V and its absolute uncertainty in meter cube. Okay, so let's look at the steps. The first step is that we have to find out the volume. Volume of a what is length times width times height. So in this case, it's 10 power 10.2 times 5.6 times 2.3, which you get 131.376 centimeter cube. So I'm going to leave the answer in few decimal point. In this case is in 3 decimal point because that's what I got, and I'm going to just leave in centimeter cube. I'm not going to change to meter cube, so I'm going to show the techniques later. Okay, the next thing, you need to find out the absolute uncertainty for the volume. So delta V over V is delta L over L plus delta W over W plus delta H over H. Basically, I'm adding all the fractional uncertainty of the measured physical quantity. Okay, So delta V over V, right, in this case is 131.376 equals to delta L, 0.1 over 10.2 plus 0.1 over 5.6 plus 0.1 over 2.3. Okay. So when you do all this calculation, you need to find out delta V and to the end, so where you will find out it, you will get approximately 9.3. Okay, so this is the absolute uncertainty. However, for the AS physics, you need to put the absolute uncertainty into 1 SF, right? So therefore it's plus minus 9, 1 SF, right? So in this case, this answer, we have to follow the decimal point or the SF of this, okay, which is, this is in terms of 10. Therefore, V is 131 plus minus 9, okay, centimeter cubes, okay. And we know that 1 centimeter cube is 10 power of negative 6 meter cubes. Okay, that is because 1 centimeter is 10 power of negative 2 meters. 1 centimeter cube is 10 power of negative 2 meter cube. Therefore, 1 centimeter cube is 10 power of negative 6 meter cube. All right. Therefore, 131 plus minus 9 times 10 power of negative 6 meter cube. And to put it in the correct format, 1.31 plus minus 0.09 times 10 power of negative 4 meter cube. Okay, so I remove the 100 from these two values and I multiply with 10 power of negative 6, I get 10 power of negative 4. And if you notice this is 2 decimal point. Okay, 2 decimal point, and this is also 2 decimal point. So this decimal point must be synchronized. Okay. Okay, I'm going to show you another method of measuring the absolute uncertainty if you're not going to use the formulas that involve the fractional error. Okay, so say example, we have this object where the length is 7.7 plus minus 0.1 centimeter measured by a ruler, and the width is say 2.21 plus minus 0.01 centimeter being measured by a vernier caliper, right? So I'm going to show you the normal process of measuring the normal, the standard technique or steps to find the area where length times width, and how do we find the absolute uncertainty, right? So in this case, the length is 7.7 times 2.31, so you will get 17.71 centimeters squared. I'm going to leave the answer in centimeters squared. Delta A over A, the fractional uncertainty for the error is the fractional uncertainty for L plus the fractional uncertainty for the width. And in this case, delta A over 17.71, delta 0.1 over 7.7 plus 0.01 over 2.31. Hence, if you complete this calculation, you find out the answer is plus minus 0.307, okay, centimeter cube. Therefore, it is, need to make it into 1 SF, so it's plus minus 0.03 centimeter So this is 1 SF. So therefore, the presentation of the answer, the area would be 17.7 plus minus 0.3 centimeter cube. Okay, so 1 decimal point, right? So if you centimeter squared. So if you want to change to meter meter square, therefore, so 1 centimeter is 10 power of negative 2 meters. So I square both sides. So I get 1 centimeter squared, 10 negative 4 meters squared. Hence 17.3 plus minus 0.3 times 10 power of negative 4 meters squared. All right. So I take away 10 from here to put it in the standard scientific notation. I'll get 0.03. Okay, 10 power of negative 3 meters squared. Okay, let's check again. 2 decimal point, 2 decimal point. All right, standardized times 10 power of negative 3 bracket meter squared. Okay, what is the other method without using this particular method? We can straight away find the error, the absolute uncertainty for A by using what is known as the range of boundary. Range of boundary, okay, divided by 2. So what is the meaning of range of boundary is that if I take the area length times width and I use the maximum value, okay, based on the uncertainty given, okay, based on the uncertainty given, and I find out what is the maximum value. I'll show you later what I mean. Minimum value divided by 2. So the maximum value is that if I add the errors, right? So which is, in this case, the area is length times width, okay? So maximum value minus minimum value, area times width. Area is length times width. So the maximum value is 7.8, right? Because that is the upper boundary of the length times with the upper boundary of the width, which is 2.32, okay, minus the lower boundary of the length, which is 7.6 times the lower boundary of the width. In this case is 2.30, okay, and divide by 2. You will find out that this is around plus minus 0.308 according to my calculator, okay. However, if you make it to 1 decimal point, okay, 1 SF, the answer you get is 0.3. So therefore, the area is 17.7 plus minus 0.3 centimeters squared, which is 1.77 plus minus 0.3 times 10 power of 0.3 times 10 power of negative 3 meters squared. Okay, so I think it's supposed to be 1.77 because this is the answer. 1.77. Right, so you can use this particular technique. You can use the range of boundary, right? But you need to be very careful with the formula that you're using. So if you're using, like example, the area, so we have to take the maximum value or what we call as the upper boundary minus the lower boundary. So you find out the answer or the absolute uncertainty is the same as the way we calculate using the standard calculation or the formula. Okay, thank you.